All right, so they're telling us about sodium vapor lamps used to illuminate streets and highways. They're giving us the wavelengths of two very closely spaced emission lines, and they're giving us those wavelengths in meters. So part A is asking us to just simply convert those wavelengths into centimeters. So you have this conversion factor where 100 centimeters is equal to 1 meter. So you can just simply move the exponent up by orders of 2 magnitude. So the answer is going to be for A, 5.890 times 10 to the negative 5 centimeters. All right, that makes sense because you're going to have more centimeters than you did when you had the same measurement in meters. So that's the first one, and the second one is going to be the same number. Also, just multiplying by 100. Okay, if you want to see the setup for that, you would just punch in the original number there, 5.890 times 10 to the negative 7 meters, and you would just use the conversion factor, 1 meter, 100 centimeters. Like I said, you're just multiplying by 100, and therefore you're going to increase the exponent twice. All right, so these are your answers for part A. Now part B, calculate the frequencies. So we have this relationship where the speed of light is equal to the wavelength, which we are given, times the frequency. So let's rearrange this algebraically, save us a little time. So frequency divide through by wavelength, you get the speed of light over wavelength. So the speed of light is 2.998 times 10 to the 8 meters per second. That's on your formula sheet. Now the wavelength that's given to us is, we're going to use the original. One second. Unbelievable how much junk, like phone calls and advertisements. Just want to get this election over with. Where were we? Yeah, we're going to use this wavelength given to us in the original problem because that's already set up in meters. All right, so 5.890. It's going to be the same numbers here, just with meters and to the negative 7. All right, so the first one is going to be 5.890 times 10 to the negative 7 meters. All right, meters are going to cancel out. You're left with hertz or per second. All right, 2.998 times 10 to the 8 divided by 5.89 times 10 to the negative 7. All right, we're going to have 4 significant figures because the wavelengths given in the problem has 4 significant figures. So our calculated answer should have 4 as well. So 5, the 0, the 8, and the 9. Now that 9 is going to round up because the next digit is also a 9 or 5 or greater. So it'll be 5090 times 10 to the 14th seconds to the negative 1. Let's save a little space. All right, so there's our answer. That's the frequency of that wavelength. All right, so now do the other one. Just going to be all right, let's set it up here. So for this one, frequency is equal to the speed of light over that wavelength, 2.998 times 10 to the 8 meters per second, 5.896 times 10 to the negative 7 meters. All right. 2.998 times 10 to the 8 divided by 5.896 896 times 10 to the negative 7. All right, four significant figures, 5, 0, 8, and the 4 is going to round up to a 5. 5085. Let me move this here. I copied this earlier because I knew I was going to need it. Just move this guy. All right, what do we say? 5085. So there is our answer for the frequency. All right, let's see what part C is asking us. So B's done. Let's go on to C. What region? All right. So that's why I copied this over. So let me move this back up a little bit. Where does that 4 come from? Huh. All right. So let's do this one here, the first one. All right, 5.89. They're both very similar, so 5.89. They're both 5.89s-ish. All right, and then 5.89 is right, and that's 5.5, 5.6, 7, 8, 9, maybe like there-ish. Orange, say orange, yellow, orange. All right, there's the answer, part C.